Thank you, Raphael. So I will continue the discussion of the functoriality of the p-adic Simpson correspondence. So the setting is the following. We have G is a morphism which is a smooth morphism from x prime to x. Of smooth S schemes. Okay, I remind you, maybe I will put it here because we need it to keep it in the blackboard. I remind you that this morphism induces, in fact, by functoriality, a morphism of Faltings topos from the Faltings topos of x prime to the Faltings topos of x, and that we have projections to the étal topos of x prime and x. This is called sigma prime. This is the morphism G, and that this diagram is committed. And I introduced last time the formal p-adic completions of these various topos. So this diagram will induce a commutative diagram of ranked topoi, which I will draw here and keep it all the time. So here we have the special fiber of E prime tilde. We take projective systems and ring it by the B bar brevi. Down we have the same thing for E, and the morphism theta induces a morphism here, theta brevi. And then here we have x prime, x S zar, OX, the formal completion of x bar. Here we have x prime S zar, OX prime. So these are just the formal completions of x bar prime and x bar. And the morphism G induces a morphism on formal schemes. And these morphisms, I denote them induced by sigma and sigma prime with a hat. Okay. Now, to discuss the functoriality of the p-adic Simpson correspondence, I need, in fact, to fix liftings, because the p-adic Simpson correspondence exists only when we have liftings. So I will fix I will assume first that there exists, and I will fix it. So deformations like this. X answer over OP OC. OC, and we have here the thickening A2 OK bar, and I assume I have deformation X tilde, a smooth deformation X prime tilde, and I also assume I'm given here a lifting G tilde of this morphism. I will discuss at the end, as I promised last time, these assumptions of liftings. But anyway, the Simpson correspondence exists only when we fix the lifting. We have a relative version I will discuss. Maybe we can get rid, or at least twist our result to get rid of this lifting, but let me write the basic result when I have a lifting like this. Okay, so under these assumptions, in fact, the construction of the period rings I introduced last time, the Hodge-Tate algebras, is in fact functorial. So for any rational number, there exists a canonical homomorphism from the pullback of the Hodge-Tate algebra down to the Hodge-Tate algebra up. I will denote it with a prime. Okay? So the construction of this homomorphism in the small affine case is rather straightforward, just playing on these deformations and the torsor definition with the torsor of deformations. Sheafifying this definition in Faltings topos is slightly subtle. I will not discuss it, but anyway, it exists. And it's well defined, canonical. I can now state the main admissibility result. So it says the following. Assume x prime to x to be proper, and let M be a Dolbeault and B bar brevi prime module on, in fact, E tilde prime S. Okay, so something up which is admissible. Dolbeau. Okay. Let me denote its associated Higgs bundle by H prime of M over OX prime of psi minus 1 omega 1 X prime over S. So this is the associated Higgs bundle. So this is an absolute Higgs bundle. I can get from it a relative one. I will denote it with an underline. So this is the morphism which I obtain just by mapping these differentials to the relative differentials. But the module is the same. Over X. So this is the induced Higgs bundle. Okay. And let me denote by, to use simple notation, let me denote by this one the Dolbeau complex of the relative Higgs bundle. Okay, so these are the notations. Then the conclusion: for any integer, there exists a rational number, strictly positive, and a C brevi R isomorphism. So I will write it and then comment it between, first of all, the cohomology of M when we extend scalars to CR. And so I will comment, I will write it and then explain the notation. The cohomology of the Dolbeau complex, relative Dolbeau complex, pull back to Faltings topos, and then extend scalars to C brevi R, okay, which is compatible with Higgs bundles, total Higgs bundles, or total Higgs field, sorry. And here, where, so first of all, this one is equipped with the zero Higgs field, QI star of M is the zero Higgs field. As usual, C brevi R equipped with PR times its universal derivation. And the most important one is this one. So the cohomology RQ G lower star of the relative Dolbeau complex is equipped with what I will call the Katz-Oda field. So this is a Higgs field on the cohomology of the Dolbeau complex, which is constructed exactly like the Gauss-Manin connection on the cohomology of on the de Rham cohomology, which means it's induced by the spectral sequence of the hypercohomology spectral sequence of the filtered complex. You filter this complex by the Koszul filtration. Okay, so this exactly the same recipe that you use for connections introduced by Katz-Oda works for Higgs bundles. Okay, so this is the main result. So maybe here's just a small comment. I remind you that this I means just the natural extension of the pullback and direct image to AND modules. So all these are AND modules. And this is an isomorphism between, so you have a Dolbeau module here, which is admissible. Okay, so a Dolbeau module, which means a B-bar Brevi module, which is admissible. You take its higher direct image, and in fact, you prove that this higher direct image is in some sense associated to a Higgs bundle. So what is this Higgs bundle? So first of all, from this M here, you go to its associated Higgs bundle, take the higher direct image, and pull it back. Okay? So this is really, in some sense, the natural admissibility result we can hope. So before I comment so maybe let me say a few words here. So in fact, this module is, so this is an OX 1 over P module, which is coherent. So I can see it as an AND module by what I explained yesterday. And this functor is in fact exact on coherent OX1 over P module. Okay, so this is just a small, important technical comment. Okay, so now, before I explain a little, comment a little bit on the proof of this theorem, I would like to state few corollaries, which maybe will make it a little bit more explicit. So the first is a little bit what I was saying before. So under the same conditions, if we assume, moreover, so if the OX1 over P module, which I just mentioned here, RQ G lower star of the relative Dolbeau complex is locally projective, okay, then the conclusion is that the cohomology RQI theta lower star of M is now Dolbeau. And there is a canonical isomorphism between its associated Higgs bundle and the cohomology of the relative Dolbeau complex, which is equipped here with the Katz-Oda Higgs field. Okay? So this is really the optimal statement. So in some sense, if you start with a Dolbeau complex here, its higher direct image is Dolbeau. And if you take the Simpson correspondence, you get a Higgs bundle here. In fact, the Higgs bundle associated to the higher direct image is the higher direct image of the Dolbeau complex of the one here. Okay? So what means to be Dolbeau? Mainly this admissibility relation, and this should be projective, locally projective. So in some sense, if I assume that this is locally projective, this theorem is exactly this state. Okay. So there is one case where we know that this cohomology is locally projective. By the way, this condition that the cohomology is locally projective is a question about rigid geometry or about formal geometry. Now there is nothing about Faltings topos, so you have a complex on the formal scheme, and you would like to know if the higher direct image of this complex are locally projected. So here is the case. So assume now that x prime to x is projective. Okay, and let, I will denote Mn be, first of all, you take the higher direct image of the constant sheaf. So I look at it as a p-adic sheaf. And then you push it forward to Faltings topos, and you extend scalars to B bar Brevi. Okay? You just take the, maybe I draw here of x prime eta bar, x eta bar, and I remind you that we have a map psi here. So you take higher direct image here, and then you push here, and then you extend to a B module. Okay, then, so these are the notation. First of all, this B bar Q module MNQ is Dolbeau, and moreover, its associated Higgs bundle is canonically isomorphic to the sum of the Hodge cohomology Ri G lower star of psi I minus n omega n minus I x prime over x, okay, where you extend scalars over OX to OX 1 over P, okay. So this is the module which is equipped with the Higgs field, which is in fact this nilpotent in this case, induced by the Kodaira-Spencer map. Namely, so this is the morphism from Rj lower star of psi minus g omega g x prime over x going to psi minus 1 omega 1 x over s tensor over OX lower star of psi 1 minus j omega j minus 1 x prime over x plus 1. So this is in some sense the map you obtain from the Koszul filtration on the Durham complex. Okay? So this is exactly what we expect. And why this, in this case, we have no extra condition in some sense? Why we know, so we know in fact that this module is locally free by de Ligne, so there is nothing, no assumption in this. Okay, another corollary. So we can have also a spectral sequence in this case. So let me now start from a local system up. So this is a ZP Brevi local system on x prime eta bar et al. Okay, and let me do the same thing as usual. Just push it forward to the Faltings topos up and extend scalars to b bar prime Brevi. Okay, assume again that x prime to x is projective. Then, and that this module MQ is Dolbeau, which means I take a local system which is Dolbeau. In particular, it could be Hodge-Tate. Okay? Then the conclusion, there exists a rational number and a spectral sequence so I will write it and then comment it. So it's an E2 spectral sequence. So first of all, you take the cohomology of the relative Dolbeau complex, as before, of the associated Higgs bundle. Then you pull it back to Faltings topos, and you extend scalars to the algebra CR, the tensor with Q. So this converges to the, first of all, the cohomology of the local system. This is now an eta local system on X eta bar. You push it forward to Faltings topos, and you extend scalars to CR. Okay. Okay, so, and as I said, this is the Dolbeau complex of MQ. Okay, so this, in fact, and by the way, you have seen that in these two corollaries, I assume that the morphism is projective. The reason is that these two corollaries used Faltings' main comparison theorem in the relative case, okay? In which case I need to assume it's projective. So this is, in fact, an immediate consequence of Faltings' main comparison theorem and the admissibility theorem I stated before, okay? So there is one interesting case, special case of the last corollary, is the case where M is the constant sheaf. And in this case, we can improve the spectral sequence I'm writing. So this spectral sequence, as you can see, it's a spectral sequence whose initial term is a coherent cohomology, okay, extend to some period rings, and its abatement is étale cohomology. So it's like a Zariski, it's like a Hodge-Tate spectral sequence. And in fact, it's precisely a relative Hodge-Tate spectral sequence. So here is the special case. So assume M now is equal. Yes? Sorry, sorry. There is his HJ. Okay, yes, sorry, thank you. Yeah, we have, it's just obtained from the previous one. Yes, thank you. Okay, so the special case is when M is equal to ZP brevi. So in this case, the spectral sequence can be in fact improved, and it follows, so the spectral sequence, I will call it by star, can be deduced from a better spectral sequence, which is the relative Hodge-Tate spectral sequence. Of G, which I will now state by just base change from B bar brevi to CR. Okay, so theorem. Assume again X prime to X is projective. Whenever you see this condition, it means that we use Faltings' main comparison theorem. Then we have a canonical spectral sequence of B bar brevi Q modules, okay, that we call the relative Hodge-Tate spectral sequence, H2ij. First of all, you take Ri j lower star of omega j x prime over x. Then you pull back to Faltings topos. You extend scalars over sigma upper star of Ox B bar brevi Q. And then you twist by minus J. It converges to, first of all, you take the cohomology of, eta bar, ZP. Then you push forward to Faltings topos, and you extend scalars to B bar brevi Q. Okay? So this is the relative version of the Hodge-Tate spectral sequence I mentioned in the introduction. And in fact, I omitted to mention something, and I apologize for this. So I already mentioned that there are two different approaches for this spectral sequence, one due to Cariani and Anna Cariani and Peter Scholze, and our proof. And there is another one, so due to Koshikawa and Gaisin. So so I apologize for this. In fact, this should come soon. The paper is almost ready, according to Rusi. He said that it's almost ready, and maybe ready, and you will see it soon in archive, I hope. So there is some similarity between our approach and their approach. Okay, so one property of this spectral sequence is that, in fact, first of all, it does not require any lifting. So here there is no need for any lifting. Okay. And the second thing, it's in fact GK equivariant for the natural action of the Galois group GK, and hence it degenerates at E2. Okay, so this is all I want to say on the corollaries. I want now to comment on the proof of the main admissibility result, which is no longer on the blackboard. In fact, the proof of this main theorem can be divided into 3 steps. So the first step is a computation of both the Galois cohomology and the Higgs cohomology of these Higgs-Tate algebras, but we compute a relative cohomology in the small affine case. Inspired by Faltings computation, we just adapt Faltings computation to compute relative cohomology instead of that. So this is a kind of local computation. Then we need to Schiffify this local computation. And to Schiffify this, we need a new geometric object. And I think this is probably the main new input in this picture, in our work. In fact, to Schiffify this computation, we consider the following diagram. So I will write it and then explain it. So, as you know, we have this commutative diagram, and I will consider the fiber product of these 2 morphisms of topos. So this topos exists, it's a fiber product, we know it exists, and this map factors like this into 2 maps. So this, I call this tau. So this is this Cartesian. So to Schiffify, the local computation I described amounts to, really leads to the computation of the following sheaf. So it leads to compute this sheaf here. Okay? And this is really the key information we need. Okay? So we need to put our hand on this topos, which is not easy. And for this, and this was the good surprise, both in the proof of the relative spectral sequence and for the admissibility result, is that we have a nice topos, a nice site which is underlying this topos, which turns out to be a special case of, in some sense, a variant of Faltings topos. It's a relative Faltings topos, which we, in fact, discovered by inspiration from oriented product of topos that the linear introduced. Okay, so this is what I will now comment, describe. I have to hurry a little bit for the hike. Okay, so the relative Faltings topos. So this will be the second step, and the third step will be a base change relatively to this square. Okay, so I will start now in a slightly more general setting. So I have a morphism between just S schemes. I will assume later that they are smooth, etc. And I define the following category. So this is the category of morphisms. I will denote them W to U and V to U above the morphisms X prime to X and X eta bar to X, like this. So I need 2 commutative diagrams, and I assume that W to X prime and U to X are étale, and as usual, V to U eta bar is finite étale. Okay, so it looks a little bit similar, just I add another square to Faltings topos. And now I equip this category with the topology. So I equip it with the topology generated by coverings of the following type. So let's say Wi to Ui, Vi, going to W to U to V, I and E. Now of three types. So the first type, I assume that Ui is equal to U, Vi is equal to V for every I in I, and Wi to W is a covering. Okay, I switch V and W, so Ui is equal to U, Wi is equal to W, and Vi to V is a covering. And the third, more subtle covering, in fact, this covering is just given by one morphism, so I will denote it with a prime instead of I. So it's something like this. I assume that first of all, W prime is equal to W. U prime to U is any morphism, but I assume that this square is Cartesian. Okay, and here I insist U prime to U is any morphism. Okay, so if you are as familiar with oriented products, this is the good definition. And I will denote by G tilde the G tilde will be the associated topos of sheaves of sets. Okay, then in fact I have a natural projection like for Faltings topos, but now into X prime et al. Okay, which is defined on the level of pullback. So if I have U is et al over X, then pi upper star of U is just equal to, sorry, I call it W because to respect my conventions, here it's, I need to go from X prime. So it's a W over X prime. So it's just W mapping to X and X eta. And I take the associated sheaf. Okay, so it's well defined. It induces a morphism of topos. Moreover, another important property, if X prime is, so if X prime is equal to X, then we have a canonical equivalence of topos between this relative Faltings topos and the absolute Faltings topos. Okay? Hence, since the construction is obviously functorial, we see that in fact our morphism from Faltings topos E prime tilde to E tilde, this is our morphism theta, which is defined by functoriality, factors automatically through the relative Faltings topos. Okay, so I will call this tau, and this is gamma. And I have here projections, first of all to X prime et al, here to X et al. This is E sigma, this is E pi, this is E sigma prime. And these diagrams are in fact commutative. Okay, now the fact is that this diagram, this square is Cartesian. Okay, the square is Cartesian. Okay, it's not complicated to see. So in fact, we have really a very nice underlying site to the fiber product. Okay, so now what we will do is that we will prove a base change. As I said, we start here. We compute the higher direct image of our period ring here. Okay? We relate it, in fact, to the pullback of the differential. This is what we prove. Now, in order to go down, we need really a base change because we pulled something here, we go down. So we need really to prove a base change relatively to this square. This is the last step. So we do it in two steps. First of all, we prove a base change for torsion abelian sheaves on X prime et al. Here, which means pull back, push forward, pull back. This is give us a base change theorem. So this one is inspired by a theorem of Gaber, analog theorem of Gaber for oriented products. And it reduces mainly to the just proper base change theorem in et al topology. Then from that theorem, we deduce the following result for coherent sheaves, quasi-coherent sheaves. And this one involved, in some sense, the almost purity, which is a combination of the two theorem. It says the following. So let x prime to x be a proper, smooth morphism of S schemes, of smooth S schemes. S schemes. And there exists an integer n, 0, such that for any small n bigger than 1 and any q bigger than 0, small n, any q, and any quasi-coherent O x bar prime, no, x prime n module. I call it F. The kernel and the co-kernel of the base change of the following base change morphism, sigma upper star of RQ G lower star of F going to RQ gamma lower star of pi upper star of F are killed by pi to the n. Pi to the n. Okay, so I have to tell you a little bit what are these pullbacks here. So in fact, these are pullbacks by morphism of ring topoi. So up pi, we go from relative Faltings topos that we ring by just the direct image of B prime, and we go to X prime, etal OX prime, that's all. And down, so just Faltings topos, we go to X etal OX. So these are the pullbacks by this morphism of ring topos. Okay, so this, in some sense, finish the sketch of the proof. We have to follow the Katz-Oda Higgs field in these base changes, but this is doable. In the last part of this lecture, I would like now to discuss a little bit the relation to Hodge-Tate local system. As I said in the beginning, I have always fixed some deformations, and this is necessary for the p-adic Simpson correspondence. However, we can get rid of this deformation by developing a relative version over S, which means what? We will replace our deformation by a relative deformation. I will call A2 OK bar over OK, which is now an OK algebra. And over OK, there is always a deformation, the trivial deformation. Unfortunately, this approach has a small defect, which I will explain, but this defect does not affect the study of Hodge-Tate local system. So let me introduce now this relative version, which is in fact a logarithmic relative version. So I fix pi, a uniformizer of OK. And I fix pi n, a sequence of elements of OK bar, such that pi 0 is equal to pi, and pi n plus 1 to the power p is equal to pi n, like I did with p, but I do it with the uniformizer. Okay, so then I get an element in the OK bar flat, just the reduction of this modulo p. Okay, now take the Vit vectors of OK bar flat, which was, if you remember, the first input to construct A2. We start with the Vit vectors. Start with the Vit vectors of OK bar flat. What I do is that, so this is naturally an algebra over the Vit vectors of the residue field. So I extend scalars to OK. And I will call this W OK of OK bar flat. Okay, now I denote, so I will define a logarithmic version of this, call it W star of OK bar flat. So this is the sub W OK bar flat algebra of the same thing where I invert, just I tensor with K. Okay, with K, which is generated by the following element. I take the Teichmüller lift of this element. I divide it by pi. Okay, so I take the subalgebra of this algebra, the subalgebra over these Vit vectors where I extend scalars to OK, which is generated by this element. Okay. And inside it, I will set, so I need a substitute for xi. I call it xi star pi. So this is the following element. So this now is an element of W star OK bar flat. So this algebra is a subalgebra of this one, which contains this element, in fact. That's okay. It's not complicated to see that, in fact, this element generates now the kernel of theta in this setting. Our theta, the usual theta, extend to another, to a new theta from OK star of OK bar flat to OC. Okay, so this is just induced by theta. And in fact, this xi star pi is in fact a generator of the kernel, like in the absolute case. Maybe I call it star OK, be coherent with my notes. So then I will define A2 star of OK bar flat over OK is just this algebra OK bar flat modulo this element generator of the kernel square. And again, this is an extension of OC by OC. It's a new extension. It's an extension of OC by OC. This is this theta star OK. This is multiplication by this one. Okay? And in fact, what is the difference compared to the previous one? So clearly the previous one maps to this one, to the relative one. And in fact, if you follow the ideal of square zero, you will see that we have a canonical isomorphism between xi OC and, so I write it and then define the terms, delta xi star pi of OC. So here this partial, this one is in fact the different of k over k naught, and k naught is just the fraction field of the Vit vectors of small k. So it means that in fact this xi depends a lot on the field k. Okay, and this is in fact the bad side of this approach. Okay, so now we can work with the two things together. So I will just introduce a notation to lighten a little bit because this star and sub indexes OK are too heavy to write. So let me denote by S tilde one of the following thickening, either spectrum of A2, OK bar, or spectrum of A2 star, OK bar, flat over OK. So we have in both cases closed immersion, thickening of order 1, from this one to S tilde. In the absolute case, there is no natural map to S, but in the relative case, it maps naturally to S. So this is the only difference. And in fact, we can develop all I said previously relatively to this closed immersion, which means if we fix a thickening over S tilde, we have a p-adic Simpson correspondence, and we have the functoriality I described before. Okay? The only problem now, so we have an admissibility condition, which means a Dolbeault condition relatively to the context we are working with. So the only the problem is that the admissibility condition, Dolbeault, which as I think mentioned already, correspond to the smallness condition of Faltings, depends now on K. And this is a big obstacle to do the descent step. Okay? So in some sense, this approach, the relative one, which will get rid of deformations because there is always a tautological deformation, is a little bit less restrictive, so you cannot get from it a correspondence for all representations by descent. Okay, but for Hodge-Tate local system, this is work. There is absolutely no problem, and this is what I would like to tell in the last part of the lecture. So I will tell it first in the affine case. So let me assume now that X is an affine scheme. Smooth. So it's first of all small in the sense of Faltings. Small affine. Smooth S scheme. Okay, so this is usually the case we start to work with. And I assume, moreover, for simplicity, that X eta bar is connected. And X S, as usual, is not empty. And I choose a geometric point of X eta bar. And I will denote, as usual, delta to be the geometric fundamental group. Okay. I will put R1, R where I extend scalars to OK bar. And R bar, as usual, is the stalk of the sheaf B bar X Y bar, which means this algebra obtained as inductive limit of normalization infinite étale extensions. Okay, so all these are, so this is a representation of pi1. Then, okay, I fix now a deformation. Okay, aussi. X tilde, smooth deformation over S tilde, which means either in the absolute or in the relative case. And relatively to this deformation, by the recipes I explained, we have first the Hodge-Tate algebra, see? And we have also variants with certain thickness, CR, it's a Hodge-Tate of thickness R for a rational number R bigger than 0. Okay? I explained in the sheaf version what means to take, in some sense, a weak completion. It means to work with all CR together. But in fact, in the affine case, we can really define an algebra, which is the weak completion. So let me define it now. Call it C dagger. So this will be the inductive limit for R in Q, strictly positive, of the p-adic completion of these CRs. Okay? So in fact, this is the period ring in the affine case for the Hodge-Tate, for the p-adic Simpson correspondence. Namely, this algebra define a functor from representations, semi-linear representations over the p-adic completion of R bar of the fundamental group, to Higgs bundles, to Higgs modules, So these Higgs modules have coefficients in R1, the p-adic completion of R1, where you invert P, and the coefficients, in some sense, of this Higgs field is precisely psi tilde minus 1 times omega 1 R over OK. So what does it mean, psi tilde? I did not define this. Psi tilde in the absolute case is just psi, and in the relative case is the psi star pi. So I call it psi tilde to work with both of them. Okay, and what is this correspondence? You take a representation and you map it to the following Higgs module. First, you extend scalars, as you expect, to C dagger. Okay? And then you take the invariance by the fundamental group. And what is the Higgs field? So this is the module. The Higgs field is induced. So the Higgs field is induced by the derivation of C dagger, which is limit of PR universal derivation of CR completed. Okay? The universal continuous derivation of CR completed. So this is exactly what we have done in the Schiff version, but written in the affine case. It's really very concrete and simpler to write. So now I can state the result about Hodge-Tate representations. So let M be a projective R bar hat 1 over P module equipped with of finite type. First of all, finite type equipped with semi-linear, an R bar hat 1 over P semi-linear representation of delta. But I don't assume anything on this representation. Then the following are equivalent. So the first property is that the R bar hat 1 over P representation M is of delta is Dolbeault. So in this context, in the affine case, this means that first of all it's continuous for the p-adic topology plus C dagger admissible. And in fact, the associated Higgs bundle is projective of finite type. Okay. And so first of all, the representation is Dolbeault, and the associated Higgs field associated R1 hat 1 over P Higgs module H of M is nilpotent. What does it mean? So it means that there exists a filtration, I will call it HI to N of H of M, such that, so it's a decreasing filtration, so H naught is everything, Hn is 0, okay? And moreover, theta of Hi is contained in psi tilde minus 1 answer Hi plus 1, okay? And the second property, so this nilpotence condition, admissibility plus nilpotence, implies the following, is equivalent to the following property. There exists a projective R1 hat over P Higgs module n theta, it's of finite type, It means that the module itself is projective of finite type, and theta is a Higgs field with coefficients in the usual module R over K. Okay, and C linear delta equivariant isomorphism of Higgs R1 R bar hat 1 over B modules from n tensor over R1 hat R bar hat and M tensor over R bar hat, sorry, tensor C, tensor C, our period ring, and here tensor C, okay? Which is, as I said, compatible with Higgs bundles. So, let me first of all comment a little bit on this statement. So to say it's a C dagger admissible, it means that we have this isomorphism where we put here H of M and we put here C dagger. Okay? It turns out that to be if the H of M is nilpotent, you can descend this admissibility relation, isomorphism, from C dagger to C. And conversely, if you have this admissibility isomorphism on C, then automatically it's nilpotent. This is easier. Okay? And moreover, you don't need even to assume that the admissibility isomorphism you have it with H of M. You can just assume that there exists an N. But as a byproduct, moreover, in this case, H of M is automatically isomorphic to N theta. Okay. So this is in some sense normal and reasonable to expect. So what we will do is that we will maybe, I have no time, so I just finish in 2 minutes. So we will define Hodge-Tate representations to be representations that satisfy these equivalent conditions, which mean just it's Dolbeau and its Higgs bundle is nilpotent. Okay? So just one last comment. So Takeshi Tsuji developed an arithmetic version of this correspondence, which applies to an arithmetic fundamental group, which means you put eta instead of eta bar. In this case, you get a Higgs field, but you get also a Sen operator, and there is a relation between the two, compatibility relation, which automatically forces the Higgs field to be nilpotent. And this remark, in fact, makes the bridge with the work of Liu and Zhu. And you will see these kind of considerations in, I guess, the lectures by Pan Luwei and Tongmu He. Okay, so I stop here, and yeah, thank you.
Okay, so are there any questions in the room? Then let me turn to the... Oh, yeah, there's a question by Ahmed Abbes.
So if you have an importance condition, does it necessarily hold that the filtration that satisfies the importance condition can be chosen to be by summons, that is direct summons or not?
No, this is even no. If you assume the filtration to be a direct factor, this should correspond to what should be the variation, p-adic variation of Hodge structure, I think. So in some sense, if you can write it as a direct sum of things, this is really inspired by the complex case and what we know about how you describe variation of Hodge structure. This should be, I think this should be the good condition on p-adic variation of Hodge structure. Here it's just a filtration. I don't ask it's direct summand.
Any other questions? Yes.
I just want to remark that in the Faltings main comparison theorem, we can replace the projective conditions by just the proper condition, by the cohomological descent of Faltings topos.
Yeah. this is I should have mentioned this. Sorry for this. So we can improve he improved this. So Tomo improved the relative Faltings comparison theorem that we proved by getting rid of the projectivity using cohomological descent.
Yeah, but reduced to your projective result.
The statement you can get rid of it. And I see a question up, so I have to.
Where? Oh, okay.
I have a very sort of vague extended question. There's in complex algebraic geometry, there's the Simpson theorem.
Yes.
Where there's a sort of bijection between representation of a group and the flat connection. Is Simpson correspondence some sort of
Yes. Yes. So the first, at the same time as Faltings started this story, Döninger and Werner started a generalization of the Seshadri-Narasimhan correspondence. Okay, and so there were kind of two parallel theories. Then Dashinshu proved that the two are the same. Okay. For curves, always in this context. So the theory of Döninger-Werner corresponds to the theory of Faltings when the Higgs field is 0. Just the Higgs field is 0. Okay? And in fact, he will also, what he will say is a kind of motivated by the Döninger-Werner in his lecture on Friday. So you can. Yeah.
Any other questions or comments? Okay, then let's thank the speaker again.